So let us discuss one of the advanced concept of kinematics. Consider a situation in which this surface is representing ground. Now this one is a surface which is at a height of h from ground. This height is given as h. Now consider a particle which is projected like this at an angle of, suppose, alpha, like this. Now, from the knowledge of projectile motion, we all know that the particle is going to hit the ground something like this. So, we are going to analyze the angle alpha for which the horizontal range of this projectile becomes maximum. Such length will be known as horizontal range, and we are interested in maximizing this horizontal range. Let speed of projection for the projectile be equal to V0. In that case, independent of the angle of projection, the speed with which the particle lands on ground, the velocity with which particle lands on ground has a magnitude which is given as square root of V0 squared plus 2gh. This can also be obtained from kinematics, but best method would be to determine this value from conservation of energy. Now that conservation of energy doesn't need this angle. So the change in potential energy due to this height is mgh, and that causes increase in kinetic energy, because of which the final speed of the particle will be more than the initial speed of the particle. So now let us use some vectors in this projectile motion. We have horizontal component of velocity something like this, and this horizontal component is just horizontal projection of the given velocity v0. The horizontal component of velocity is going to be v0 cos of alpha. Now the vertical component of velocity is going to be v0 sin alpha. From the knowledge of our projectile motion, we know that the ball during its projectile motion will keep its horizontal component of velocity constant, and as the particle ascends height, the vertical component of velocity will decrease. I have represented this fact by using smaller arrows, and as the particle further reaches some height, its horizontal component of velocity will remain as it was, while the vertical component of velocity has completely diminished. Now, maximum height I am assuming it to be here, and then after the particle has reached maximum height, the particle will still continue to move horizontally with velocity of v0 cos alpha. However, its vertical component of velocity will start to increase, but in downwards direction. As the particle moves further, its horizontal component of velocity, and every single time I am representing all horizontal components to be same, and then it is moving downwards with continuously increasing vertical component of velocity. The vertical component of velocity at maximum height was 0. Initially it was v0 sin alpha, and as it reaches bottom, its vertical component of velocity is much more than v0 sin alpha. Now let us consider all these velocities, which were the instantaneous velocity of the particle at various positions. At topmost point, the velocity became horizontal, completely horizontal. So let us consider all these individual velocities in a separate diagram, and let us see what can we learn from this. So this is the point, and this vector is representing the initial velocity, suppose vi. This one is having magnitude of v0. This vector has magnitude of v0. Next, as time passes, suppose a time of delta t passes, during this time interval of delta t, there is change in velocity of g times delta t, which is directed downwards, because of which the final velocity after time delta t is becoming something like this. It slightly changes its direction. Now, as we can see, these two lines must share common horizontal component. This is because there is change in velocity only along the vertical direction. So this vertical component of change in velocity g delta t is going to increase something like this. and after further passage of time it will further increase, so let us change it slowly and see what is going to happen. So after suppose 2 times delta t, the change in time interval has become suppose 2 times delta t. Then in that time interval the new velocity is going to be something like this. Horizontal components of velocities of initial and final values will remain same. As time passes, the change in velocity is further increasing. As time further passes, the change in velocity is further increasing, because of which the various final velocities are these ones. So let us further finalize this diagram. So this was the initial velocity vector given by this vector, vector vi. And suppose in the very first diagram we have time of flight as capital T. So if time of flight is capital T, so in this new diagram during a time interval of delta T, such is going to be the change in velocity. So this vector has magnitude of g into t. Alright. So this final velocity vector is shown like this with final velocity of vf. So remember that this magnitude is v naught, while this magnitude is square root of v naught squared plus twice of gh. We must keep in mind that the horizontal component of velocity has never changed. This is representing suppose horizontal component of velocity vh. So this is very interesting diagram because this diagram leads to various explanations. See, so we have a triangle whose area is given as vh multiplied by g multiplied by capital T into half. So I used half of base into altitude to find area of this given triangle. So this area completely matches up with range. Why so? Because range is determined by multiplying these two factors VH and T. So this must give me range. So the thing to observe in this diagram is area of this triangle is directly proportional to range of the projectile. What do we mean by this range of the projectile? So we have range represented in this diagram like here. So this range is proportional, coming out to be proportional to this area of this particular triangle. What I mean by this proportionality equation is that if area of the triangle increases, range value must also increase because the value of g is always a constant. So that half of g behaves as a constant, and hence we can say that if we want to increase the range, geometrically we should be increasing area of this given triangle. This triangle's area if increases, the range of the projectile motion, corresponding projectile motion will increase. So let us remove everything else and we have this equation. So we'll be using this particular equation to determine the maximum possible value of range with given situation. So area, we have this area directly proportional to range. Now next, let us remove this. We just need to perform a construction. So just like this vector vf vector, I am drawing another similar to this vf vector. We also have another vector vf like this, and a similar vector according to this initial velocity vector. Let us redraw another vector like this so that parallelogram gets complete. So this one became v initial vector, and this area which was area for triangle, so this area if multiplied by 2 becomes area for the parallelogram shown in this diagram. So the area I'm talking about for the parallelogram is this one. See, this complete area is the area of parallelogram, and which is twice the area of this triangle. Now we will use another geometrical concept. That concept of geometry that we will be using is, if we have a parallelogram like this, then with given lengths of sides L1 and L2 and this angle as variable angle suppose theta, then for what value of theta is the area of this parallelogram going to be maximum? Assume that L1 and L2 remain fixed, and with given fixed values of L1 and L2, for what value of theta is the area going to be maximum? Now we can easily observe the fact that if theta is varied, the parallelogram will turn into a rectangle to give maximum area, as can be easily seen from the geometry. So this rectangle, this particular rectangle is going to give us the maximum area. This rectangle is going to give us the maximum area, and for that rectangle theta must become 90 degree. Again, using the same concept in our previous analysis, in which initial velocity has fixed magnitude, final velocity had fixed magnitude. Remember that final velocity doesn't depend from the angle of projection alpha. So even if angle of projection alpha is changed, final velocity's magnitude doesn't change. So we need to find for what value of angle alpha the range becomes maximum. We just observed that for a given set of values of sides of a parallelogram, the area of the parallelogram becomes maximum for theta equal to 90 degrees. So using this fact, we can clearly state that this complete angle must be equal to 90 degree to keep the range of the projectile motion maximum. So if this angle becomes 90 degree, this angle was given as alpha. Let us remove everything else. Alright, if angle alpha is shown here, and this complete angle being 90 degree, we have this angle equal to 90 degrees minus alpha, which makes this angle to be equal to alpha itself. Hence we can finally claim that the value of tan alpha I am going to determine without using all these angles, only by using two angles, this angle alpha and this fact that this angle is 90 degrees. So tan alpha can be written as Vi magnitude and then divided by Vf magnitude. And the values of initial velocity magnitude and final velocity magnitude, we have already determined it from energy conservation principle as V0 square plus 2gh and in whole square root, and initial velocity had a magnitude of V0. So we are directly using it to say tan alpha must be equal to V0 divided by square root of V0 squared plus 2gh. So this is the angle of projection. This is the angle of projection for which the range is going to remain maximum. So that angle alpha is finally written as tan inverse V0 divided by V0 squared plus 2gh under square root. So this concept is derived, so we can verify the result by considering a very easy situation in which we have a given ground and a particle is projected with a speed again V0, but the particle is projected from ground and it lands back on ground only. So in this case, range must be maximum for a given value of theta, and that theta is to be determined using the same formula with keeping h equal to 0. So if we keep h equal to 0, this gives us V0 divided by V0, that makes the angle theta equal to 45 degree, which is very trivial result which we just verified from the derived result. So let us use this derived result in solving questions, and let us see how this equation simplifies various questions. Now this is the question coming on your screen. Go ahead and pause this video and try attempting this question on your notebook. We are now going to solve this question. We are going to attempt to solve this question by just using the previous concept just developed. So in this question we have a particle which is projected from a height of 35 meter with speed of 30 meter per second. We just have to find the maximum possible horizontal range of the projectile on the ground. So we have already developed such concept. So let us try to solve this question. We have a surface which must be at some height from ground. So that surface, as given in the question, is at a height of 35 meters from the ground. So this height is 35 meters. The particle was projected and the angle of projection is not known. The speed of projection is given as 30 meter per second. So with this given speed of projection, the ball lands on ground somewhere here. Then in that case, the speed with which the particle hits ground can easily be determined using that energy conservation formula that gives us 30 squared, and then plus we are simply assuming g to be equal to 10 meters per second square. So using that acceleration, 2 times 10 times the height, which was 35 meters. Using this formula, we obtain the speed with which the particle lands on ground as 40 meters per second. Now this velocity is the final velocity of the particle, so we can easily determine the angle at which the particle must be projected in order to keep the horizontal range. This is the horizontal range. This is the horizontal range for the particle during its projectile motion. That angle alpha that I just mentioned, this angle alpha, the value of alpha for which the horizontal range is maximum, that we have just developed the concept for, is tan inverse of the speed with which the particle was projected initially, 30 meter per second, and then the speed with which the particle lands on ground as 40 meter per second. So the values must be written in numerator and denominator as 30 meter per second and 40 meter per second. I have omitted the unit so that they get cancelled. So the value of alpha is simply equal to 37 degrees. So using this angle of 37 degree, we can easily obtain the horizontal and vertical components of velocity. For the initial velocity, we get horizontal component of velocity and vertical component of velocity as 18 meter per second, and this one becoming 24 meters per second. So using this 18 meter per second vertical component of velocity, using this minus 35 meter of vertical displacement, and the acceleration equal to minus 10 meter per second square, we can obtain the time of flight by using the very basic formula of s equals to ut plus half at square, according to which this is the displacement and it must be equated with 18 times t. 18 meter per second is representing the vertical component of velocity, which we are assuming positive because this velocity is upwards. I have assumed vertically upwards to be positive, and hence I am assuming vertical component of acceleration as negative value 10 meter per second square. I have already mentioned this minus here, and after that we have this t square. So the value of t can easily be determined using this equation, and the value of positive value of t is coming out to be equal to 5 seconds. This 5 seconds of time of flight will give us the horizontal component of displacement, which will also be equal to this range. So this range finally comes out to be equal to 120 meters, and this range is representing the maximum possible range. So I hope you learned something. So if you like the content of this video, I'll request you to not like or subscribe, but I'll request you to share with your friends who are really good at physics. Alright, thank you so much. This was Asheshanandacharya.